So today we're going to be talking about kind of the second part of where we left off last time, which is numerical solutions. All right, so before we get into that, just one, I guess, announcement or maybe kind of info for you. So on homework 2, if you've already started it, you'll find that you need to use Maple for this, okay? And you might get to a point in Maple where you get a solution that looks messy, right? It's kind of this big expanded solution. That's intentional, all right? Not that I want messy solutions, but that you want to be able to use Maple to get a solution that you otherwise wouldn't be able to derive by hand and then figure out how to implement that in whatever tool you're going to actually solve the problem. So just so you're not like totally thrown off when you get to the point, I just kind of wanted to show you what I got and what it looks like and how you deal with it. Okay, so my solution looks like this. All right, so there's a bunch of, after you enforce the boundary conditions, you get a bunch of stuff. This is the solution for the constants. Right, so you can see I've enforced the boundary conditions. C1 is equal to that whole mess. If you look right here, C2 kind of in the middle. C2 is equal to that second bit. So you don't really care that it's messy as long as you can get it from Maple to the place where you want to actually solve it. So fortunately, Maple's set up so you can actually just come in here and copy this stuff. Right, so if you just select it, Control C, paste it in ease or wherever you're going to solve this, that's totally fine, right? That works. Some things that you might run into are minor kind of naming things. So ease in particular won't let you start a variable with C1 or underscore, sorry. So you have to go through and rename any instance of underscore C1 to maybe C underscore 1, right? The other thing that you might run into is as you're solving Bessel functions, you don't know a lot about Bessel functions right now. Just treat it like it's another, trigonometric function like sine or cosine is something that you call, you get an answer back. But you'll want to, I think, name it appropriately. So Bessel I has to be like lowercase Bessel I in order to get it to work, at least in I think MATLAB, that's the case. So anyways, you can basically copy this stuff, make some minor substitutions, and then just use it directly. Right? I just wanted to let you know that, so you're not like totally thrown off by that. Okay, so that's kind of the only thing up front, and let's then get into it today. Okay, so like I said, we're going to be talking about numerical solutions. If you remember, this is our example from last time. We had this thing called a current lead. It's just a big wire that's taking 1,000 amps of current and moving it from high temperature or room temperature down to cryogenic temperatures. Our goal here was to design the wire so that there is conduction through from the hot to the cold, just because it's such a big temperature difference. You are getting conduction from the wire into the cryogenic destination, right? But we want to minimize that. So we were trying to design the diameter of the wire to kind of find that sweet spot. So last time, you remember we did this in ease. We developed a set of equations. We discretized the domain into a bunch of nodes, had equations for that, implemented that in ease. And then we left off saying ease is probably not the best place to do numerical solutions. So what should we actually do? So today we're going to talk about 2 other options. Both of them can use, well, one in particular is really good with MATLAB. That's matrix decomposition. MATLAB's really good at matrices and inverting them. So matrix decomposition takes advantage of that. The second one is really one that you can do anywhere. So if you have any programming language, Python, or you could do it, we'll do it in MATLAB just because it's easy, but you can do it anywhere, right? And it's called Gauss-Seidel iteration, sometimes also called successive substitution. So these are 2 techniques we'll go through. Okay, so let's see, we remember where we left off then. So the first thing we're going to talk about is matrix decomposition. All right, matrix decomposition. The idea is that we went through all this trouble to set up this numerical model, right? This set of algebraic equations. And the set of algebraic equations has an interesting and important property in that it's linear. What does linear mean? In this context, it means that if you look at every place that t appears, t is only multiplied by constants. It's never multiplied by itself. It's never multiplied by another variable. Okay, so you can see if you look through these equations, we see, right, K, AC, those are constants, at least at the position we're evaluating them. Right, AC may be changing in some problems, but we're evaluating it at a position, which means it's constant at that position. Okay, T2, T1, these are all just multiplied by things that are constant out here, things that are constant here. And then over here, we have a term that's not a function of temperature at all. It's just a constant itself. Right, and for this particular node. Right, so we can take this unique property and put all these things that are multiplying temperatures, these constant terms that are multiplying temperatures, into a big matrix. Right? Once we have it in a matrix, we can invert that matrix and solve the equation, and we get back the actual answer that we're going for, the temperatures we're trying to solve for. Okay, so what's an example of this? I mean, you know, a really simple example, you could think of maybe a set of equations, or just write some really simple equations, you know, 2x1 plus 3x2 plus x3 is equal to 1, right? That's one equation. So if we had three variables here, how many equations we're going to need to solve this? We need 3. So we'll just write something out here just for sake of example. X1, 5x2 plus x3 equals 2. And 7x1 plus 1x2 plus 2x3 equals 5. Okay, so this is a set of equations that we could solve. And you, from your prior coursework, you should maybe recognize that we can take, we have 3 variables here, each of them in their own column. We can take the coefficients on those variables and put them in a matrix, and we'll call that matrix A. Right, so A might be this big matrix, and it would be 2, 3, 1, 1, 5, 1, 7, 1, 2. So 1, 2. Right, and this is our matrix A. And we denote that it's a 2-dimensional matrix with the double underline. Okay. The second part of this is we have variables, x1, x2, and x3. Those would be in a column vector. And we'll call that x single underline, so it's just a vector. And then those things have to be equal to the constant, right? The other remaining part of the equation. In this, it's 1, 2, and 5. Right? So if you look at this, this is just another way of writing the exact same thing. If we went through and did our matrix multiplication, we took this vector here, x, did our matrix multiplication on A, we would get back exactly this set of equations, right? So the same idea applies here, where we want to take our temperatures that are now our x values, put those in a vector, collect any coefficients on those temperatures A, and put them in A, and then have anything left over that's constant, that's not multiplying temperature, and have that in B. Okay. So let's look at this for our problem here. Right, here's our problem. Again, the goal here is to take this and get it into this form A x equals B. Right, and for this, what we're going to say is A, I, J. That's the ith row and jth column of this A matrix. Right, that's going to be the coefficient in equation I. Equation I that multiplies unknown J. Okay, so we're taking n equations, and we number those equations 1 through n. The ith equation in that sequence, the A coefficient in that ith equation, that's multiplying the jth unknown. So that might be t, j or whatever. That would be going into that position in the matrix. Okay, B I is just the constant. Right, the constant that's left over for equation I. For equation I. Our x vector is easy. It's just our temperature. So x1 is T1, x2 is T2, and so on to xn equals Tn. So that's our x vector. And then, yeah, the goal is to then just get it in this format where we can use canned software to solve this, right? Like if we have this there's tons of software out there that can solve it. Like I said, MATLAB's really good at dealing with inversion of matrices. So, okay, so let's take this a step further and actually do this for this problem. Okay, first we're going to look at, remember we have we have our three sets of equations. We have node 1 on the top, node I in the middle, and then node N on the bottom. So we have to do this for each equation that we've derived previously. So this is all just algebra, and it's pretty straightforward. But what are we looking for here, just so you can kind of see how it looks? All right, so if we take this equation, what are we doing to get the coefficients multiplying the different temperatures? So let's start with T1, right? So T1 is going to be multiplied by what? So in the first term, we have minus KAC over delta X. And then in the second term, we have minus AC over R double prime C. Right, so that's the stuff multiplying T1 in this equation. Okay, T2 is plus T2. And we have just KAC over delta X. The easiest way to make mistakes on this is to forget about the sign. Okay, so always remember that, this is obvious, but remember the sign when you're including stuff here. That's always where people mess up. Okay, so that's for T2. And then what's our B part of this equation? Everything else that's left over, we have to pull that out and then move it to the other side of the equation. So for this, that becomes, let's see if I can fit it in, minus AC times TH. TH is a constant. It's not one of the temperatures in the network. Divided by R double prime C. Sorry, I'm going to fit this in. Minus rho E times delta X over 2AC times I squared. Okay. So that's the first equation, right? And you can see we have now stuff multiplying T1, stuff multiplying T2. Those are our A11 and A12 coefficients. And then we have B1 is the stuff on the right-hand side, right? You can do the exact same thing for the other ones. I don't know if we need to go through it entirely, but we would just start writing a term here. So here we would say, first let's collect everything on TI. Right, so TI is going to multiply minus KAC over delta X. And then in the second term, it's also multiplying that same thing again. Right, so this is actually times 2. We have again multiply minus KAC over delta X. Okay, so we have that plus TI minus 1 times something plus TI plus 1 times something, right, equals B. So you just do the same process, right? And we end up collecting the terms. For this example, it's pretty easy to do that. Like we can just by inspection do that. We know what we're looking for. In some circumstances, you might find that it's pretty messy and you want some help doing that. So you can actually do this in Maple. So let's look at Maple. So I've written a little program here that does this. So we're going to restart, clear everything out. And then what we want to do is write expressions for each node using the collect function. So there's this function called collect. And the arguments there collect the expression you're trying to manipulate, comma, the set of things that you want to collect around. Right? So what that means is, right here I've written collect. I wrote this expression. This is our node 1 equation. So I'm going to collect everything in node 1 around these things that appear in node 1. So you're basically trying to solve out everything that's multiplying these things you're telling it. So you put it in curly braces, a list of things that you want to collect around. Right, so here's our equation. This is what we just had solved kind of originally. And we use this thing collect. Right, so collect will then automatically do all this for you. It's really nice, right? So now we have all that stuff we decided multiplying T1. The second term is what's multiplying T2. What remains is now minus B. Great. So you can use that, and it's probably going to save you some time. So we do that for all of these, collecting the terms. Again, you see that, right? Minus 2 KAC over delta X. That's what we just said. For the nth node, it's the same thing here. And then you can just take those and multiply in the coefficients.